guys survived the first test. Congratulations. 5 weeks. And anybody get to go home this weekend?
Yay!
Yeah. So congratulations on that. I hope you didn't bring anything back so we can go home again. Yeah. Right. So be cautious. I mean, don't get me wrong. You should spend time with family and those types of things because, hey, they're the most important people in the world, right? So, or at least yours is to you, I hope. But welcome back, and we're starting a new segment today. All right. So we're going to start, and the next test will be over chapters 4, 5, and 6. And chapter 4 is actually the beginning of what I do. Okay. Don't get me wrong. We still need the information from chapters 1, 2, and 3 to be able to practice chemistry. But we're going to start looking at quantities and those types of things. And I'm a quantitative chemist, I'm an analytical chemist, and we count things. That's what we do for a living. So this chapter is, it's part of what I do. So I'm saying that out loud before we get there. And then when you get to organic chemistry later on, it's what Dr. Eason does. All right. Did I make that sound negative? It was intentional. I was just messing. Organic chemistry is fun too, and then we'll do some chapters on energy and those types of things, and that's what Dr. Bro does. So kind of outline that different faculty have different strengths. So anyway, housekeeping. The tests are being graded. They should be done tomorrow if we can get them recorded. Lab 2 is almost done. There's a couple of them that some content was missed, and we're finishing those up, but they're mostly recorded and should be back maybe tomorrow too. Just to let you know that I was hoping to get that back within a week by Friday. We did not make it, but we started grading on the test instead, so we would finish that. And so we'll circle back and get those done. Right now, you should be reading chapter 4, right? So in terms of where are you going, the lecture video is up. There is no lab video for this week and no lab quiz. So this week's lab is a demonstration lab, and so I decided just to do it all as we walk around campus. We're going to go through the water treatment plant, take a hike, wear good shoes, and we're going to go down and sample water out of the creek. And so, and I'll show you some methods that are utilized for environmental work. And it's a nice week. It's kind of a break from what we've been doing. And I used to do this only for my intro chemistry class, and a couple of my student workers were like, well, you can't do this for just your intro chem students. Your general chemistry students need to see this too. Now, if you've had intro chem, then you've seen this tour. But it's a nice experience anyway, okay? So just let you know that. So you'll see where your drinking water comes from. And how they treat it, those types of things. Yes?
At the end of the class, could you go over the table again, like how to create the table?
For the graph?
Yes.
For the lab this week? Can you go back and watch the video?
Yeah, I can go.
Yeah, so I just recommend that. And if you need personal help, then come by the chemistry department. Have you guys anybody been utilizing the chemistry department services? How are those kids upstairs? Yeah, give them thumbs up. Yeah, they try to be as helpful as they can. They remember what it was like to be you and the frustration, and we're trying to alleviate that. So we don't want you to be frustrated, we want you to be learning. And, anything else? Any other housekeeping? No?
I got a question.
Yeah, yes, sir.
We go into the lab up there and check our grades anytime, or do we need to do that?
You can go get those papers anytime. Check the lab drawer. Is that what you're asking?
Yeah.
If you want to see if we have returned any papers, then at any time there when the lab is open, usually 7 in the morning to I think the doors unlocked through 7 at night, 6 at night, 7 at night, something like that. Or if you were up there doing a study session, one of our lab assistants could actually let you into that door. Someone would have to go with you because you can't be in the lab by yourself. So
okay, so you have to get somebody to go in there with you then.
yeah, well, technically, you're just going to get papers. It's probably all right, but late in the evening, we would want somebody to go with you. Does that make sense? That's what it all is. Yeah. Anything else? Has everybody found the filing cabinet? Anybody not found it? Good. All right. Then And let's start the new chapter. And quantities of reactants and products. So we actually started last chapter looking at writing a chemical equation, right? And so this chapter begins with looking at different types of equations and defines what a balanced equation is, representation of a chemical reaction which uses coefficients. What do the coefficients represent? When you think about it, molar ratios. Yeah, so it's a balance of the reaction based on moles, represented the relative amounts of reactants and products, right? And so I like to look at that as those coefficients are representing moles. And so we can do cool things with moles. All things are possible through moles, just to let you know that in chemistry. That sounds kind of funny. So we have a simple mathematical problem. How much H2O in moles results from burning in excess of H2 in 3.3 moles of O2? How much moles in, or how much H2O in moles results from burning excess H2 in 3.3 moles of O2? How do you set this up? What do you need first?
You need the equation.
You need a balanced chemical equation, don't you? And so, you guys have written this one before, see if you can beat me to it, right? What are the reactants?
Hydrogen and oxygen.
Hydrogen and oxygen, H2 plus O2. And what do they yield? H2O. And is it balanced?
No.
No, if we double the hydrogens on either side, then that makes the oxygen match up, right? You guys with me? Now, how do I use this to answer this question? Now, I have a question. We did this in lab. There's a term that should be applied to this problem. Which reactant is the limiting reagent? Which reactant is the limiting reagent? The oxygen is, because what does it say about the hydrogen? You have excess. So if I have an excess of a reagent, that means that we have more than we need, right? You guys with me? So that means I'm limited on the oxygen. So I'm starting with 3.3 moles of O2, right? And now I'm going to use the conversion factor that I get from this sentence, right? I'm going to convert it to moles of what? H2O, right? And so if I have times 2 moles H2O divided by 1 mole O2. You guys get that, how I did that? Just pulled it right out of the sentence. Okay? I made a conversion factor. Could I get to moles of H2 that would be used in the same fashion? Yeah, we'll do that one here in a second. I'll let you finish that calculation. What's 3.3 times 2? Equals 6.6 mole H2O. And so, yeah, how much hydrogen, tell me how much hydrogen was needed. Is it the same math? How much hydrogen is needed to consume 3.3 moles of oxygen? 6.6. So you set it up exactly the same way. 3.3 mole O2 times 2 moles H2 divided by 1 mole O2 equals 6.6 moles of H2. So that means in the reaction, we consumed the same number of moles of hydrogen and made the same moles of water. Now, I have a quick question. I want to take this a step farther. Right? How many grams of water did we make? How many grams of water did we make? How do I get there? I've got to go to the periodic table, don't I? And get a conversion factor. And so the conversion factor for water, right, from moles to grams would be what? Somebody said 18. And just a reminder how we got that. We have 2 hydrogens, right, times 1 gram per mole. And we have 1 oxygen times 16 grams per mole. And this equals 2, this equals 16, and that is 18 grams per mole of H2O, isn't it? Okay, so this is a conversion factor, and so if I take my 6.6 moles, we're going to do this, we'll do this right up here. So if I take my 6.6 moles H2O times, I got to set it up to where moles cancel, right, to get to grams. So I would multiply times 18 grams per mole. And this equals what? 118 point what? 8 grams H2O. Okay? So these are calculations which I want you guys to learn to do. Right? Literally, we're going to work until we get the handle on this. Okay? So now I gave you bonus material right there. I worked ahead when I did that second part. Okay? This first part just covers the moles. Cool? But I want to connect those all along because that's really how these calculations normally go. That's where we would go, what direction. And so this is just showing that setup and showing the mole ratio circled up there. And so that's from the balanced chemical equation. All right? So we get that up here. And then we get the molecular weight to get back to grams from that position. So, all right. There's a balanced reaction. And so this one is showing a cartoon of the reactants on this side. And so it's showing H2 and Cl2. Dr. Easton actually does this reaction for you guys in organic chemistry as a demo. So just let you know that he enjoys this one and or at least has done this one in the past. I have gone to watch because you're always curious about those things. And so H2 plus Cl2 yield 2 HCl. And so we see the balance 1 mole of H2 to get to 2 moles of HCl. This is the one place in the world you guys realize that 1 plus 1 in this case equals 2, but it is not always that case. We can have 1 plus 1 yielding 3, or 1, or it's the weirdest math in the world. Well, because it really doesn't work that way. Okay? It's not really an addition, it's a ratio relating those. And so, yeah. So these are showing different types of reactions that we're going to see. A combination where 2 things come together to make one. A decomposition like electrolysis to make 2 things. A displacement where the yellow one comes in and bumps the red one. And so we get the green, yellow, and plus a red. And so that's a displacement exchange where partners exchange. Now, something about exchange that you should always talk about is that when I have this situation, it's ionic, right? And the yellow goes with the blue, right? Because the negative one is always second, right? And then the red one goes with the green, and you notice that red goes first because it's more electropositive, okay? And so you'll get to see that, and we'll look at examples of all of these, okay? So synthesis or combination reactions, the first one here, combination reaction. And this is actually showing one. And this is one we'll do for you in a demo show. All right, we have one, and I'll try to get Dr. Bro and Dr. Easton to come down and put it on for you guys this semester. And This is zinc metal plus I2. Now we have to figure out what ion is zinc going to make. It's in the transition metals, isn't it? So, what are we going to do? Is there a page in your book where you could go look right now? Or a slide? I'm asking
They had some of them.
because you need to be able to find those when you're not ready.
Yeah, close to.
Now, which page is that on?
That's 91.
91. I was at 93. I was close. So there's a table right there in your book. There's also a slide that shows the same things, right? Would it be a good idea when you're doing this to have that available to help you learn these? Okay, so I would go back into that chapter and grab that because you're going to need these. We're going to do a lot of reactions and have to know what ion forms. Okay, now it's easy when we don't have transition metals, isn't it? Because you can just use the periodic table for your main group metals, your alkali metals and earth alkaline metals, and the main groups over here on the right until you get to the bottom. And then they can get confusing too. So anyway, if we're looking at zinc, then zinc makes a +2. So what's my product? Now, there's something interesting about this reaction. I think this is the way it happens. But if I'm looking at this, then what's the purple? What's the purple? Do you see a gas in that reaction? It's actually vaporized iodine because the reaction is very exothermic, right? And so it produces a fog of iodine. When they do this, they usually do it in a bottle so it traps the iodine. And they can call it genie in a bottle, right? Yeah. So it's a nice demo, in my opinion. It's one of Dr. Isa's that he does. You can't steal your colleagues' demos, right? Because, yeah, poor taste, right? I can't. Oh, I'll do something, I promise. All right. Decomposition reaction. So what was the first one? Let's get the name of that. Combination, and that's where two things become one. That's easy, right? Decomposition, one thing becomes two or more. You guys with me? Two or more. And so decomposition reactions, X, Z goes to X plus Z. And electrolysis is a place that this happens very commonly, where we can take our water reaction we had on the board earlier, H2O goes to H2 plus O2. And so we can do that by adding electrons. And in fact, there's some people believe that this is maybe the future of energy. Okay, instead of combusting fossil fuels, that if we would take water and make hydrogen gas, right, that we could then combust it or use other types of reactions which can harness the energy, right, like a fuel cell. And if we use hydrogen, then what's the byproduct? The reverse of this reaction. Water, right? So you take water and make hydrogen, and then you take the hydrogen, use it for energy, and there is no pollutant. The biggest problem, though, is the storage of the hydrogen, right? Because it's a gas, and we can't compress it enough to take the same fuel density as we can get with a liquid fuel. Right? You guys with me? Or if I go to super high pressures, does it become dangerous? Yeah, I can. So right now we don't have that capability to do that. Now there's other ideas about storing the hydrogen in a chemical fashion and then releasing it from that chemical storage. So anyway, now this is a fun molecule right here. This is nitroglycerin, that one's nice. It's 3 nitro groups on a carbon chain. What do we know about nitroglycerin? Boom, yeah, it blows up. I mean, there were numerous lives lost over nitroglycerin. In fact, the development of trinitrotoluene and dynamite was out of that. The brother of a scientist named Nobel, you guys recognize that name? Yeah, he lost his brother to an explosion in the lab making explosives for mining industry, those types of things. And so he set out to make a safer explosive. Okay? And then amassed a huge fortune, and now that fortune lives on, is awarded a number of science awards and literature and so on. And so anyway, the reaction down here, do you guys see the decomposition? So this is trinitrotoluene, TNT, and 3.5 COs, 3.5 carbons, 2.5 H2Os, and 1.5 nitrogen gases. So it goes from very condensed here in a solid form or liquid form, and it expands. All of those are gases, and so you take it from a very small place to, well, how many moles of total gas are made? How many moles of total gas? 11 moles. And so you go from this size to, in the gas phase at room temperature, 22 liters per mole. So how many liters? 22 times 11? 231 liters at room temperature. Now it's actually at high temperature, so it's even expanded more than that. So probably a 30-liter volume expansion from the reactant to product. Do you understand why it destroys things now? Those molecules are accelerated out instantaneously and expand, and so, yeah, they blow things up. All right, and I actually talked about electrolysis a little bit over here with this reaction. I did it out of order. Decomposition caused by an electrical current, and I have an anode where oxidation occurs and cathode where reduction occurs. I always remember anode and oxidation for electrolysis. They're the same, both vowels, and then cathode and reduction are both constants. That's how I remember it for electrolysis. Here's a device actually doing a reaction over on the board, and so this is showing a battery, and that battery is hooked up to 2 electrodes. Now you want to make sure those electrodes are inert if you're going to do this. What does inert mean? They're non-reactive. Now they have to be conductive, right? So inert means that they're not going to participate in the reaction, all right? Now, you can actually do this and the electrodes participate, trust me, because I set this up one day and dissolved some electrode in the process and made a cool solution. I did not get the magical volumes here. Wait a minute, what do you mean magical volumes? It's not magic, actually. What do you guys notice about the volumes right there? See the gases right here? Is there more gas, more of one gas than the other? Can you look at the balanced chemical equation over here and tell me which is which? Hydrogen has 2 moles of gas for every 1 mole of oxygen. So when I'm looking at this picture shows that more hydrogen is being produced than oxygen. Because gases at the same temperature occupy the same space by mole. Right? You guys with me? By mole, the gases at the same temperature, unless they're, well, behaving as ideal gases. Okay? And so at room temperature, these behave as ideal. Now, the hydrogen is actually more soluble in the water, or will move out faster because it's smaller and it has more velocity, right? So it has a tendency to escape some. Although in that situation where it's inverted, it would retain it. But anyway, cool stuff. Any questions on what type of reaction was that? It was a decomposition reaction. So I have combination, I have decomposition, and now we're going to look at displacement. So this is where a reaction of a compound with an element to produce a new compound and release a different element. And so in a displacement reaction, for example, I have sodium metal and H2O, and when I react those together, I make sodium hydroxide, okay, and hydrogen gas. Now, this is showing a picture of it. I'll let you see this live and in person, all right? So just be aware it's coming to a classroom near you, right here, in the future. And so this is just showing that reaction. Why is it on fire? It's highly reactive with water, and that reaction, there's a word for that, is highly exothermic. Yep, you said exothermic? Good job, right? And it's so exothermic that what does the hydrogen do? It catches on fire, doesn't it? And so you're seeing that happen in that beautiful picture right there. All right? And there's some great videos of this on the internet too, where they drop big blocks of sodium metal into water, and yeah, it's quite amazing. So if you're interested, take a peek. All right. Oh, I should have done the reaction. I did do the reaction, didn't I? Yeah, I did that. All right, the last one, exchange. Reactions where ion partners are exchanged. In fact, we've actually looked at some reactions that do exchanges, okay? And what's going on is literally the partners switch places. We're about to do a couple more in a analysis. But here's one where there's an exchange that's going to happen. And so I'm going to let you guys try to complete this. Okay? I'm going to let you guys try to complete this, and I'll do it on the board here in a second after I give you a chance. What's your first job to do here? Figure out each ion, right? Separate them into ions, and then switch the positive from one to the negative of the other, right? And vice versa. All right, are you using your periodic table right now? You should be, yeah. Well, you can on the right-hand side, but that left-hand compound is a little more complicated, isn't it? So would that little sheet which has the oxidation states be helpful? Yeah, and maybe a list of polyatomic ions too, right? Because there's a polyatomic ion on there. If I'm looking at that though, I automatically, from my training, see copper 2+, right? And that means SO4, and it stays together, guys. This does not come apart. This is a polyatomic ion. SO4 2- has a name. What's the name of it? Sulfate ion. And so it's SO4 2-, right? Plus what? Barium. What you do with an old chemist. Plus what? I broke those apart and made, in fact, I've made the ionic expression here, right? And this is the total ionic expression. And then this yields, and I'm going to move down to right here, okay? Well, what does it yield? Copper what? Copper Cl2, and I'm going to put some letters behind that, okay? Most halides are soluble, okay? and barium sulfate precipitates out. Okay? That's what drives this reaction to happen. And so when it's aqueous like that, that means that I've still got Cu2 plus, right? And Cl minus. What's that?
Why do you do 2 Cl minus?
Because if you'll look up here at the barium chloride, so I can't lose atoms. They don't go away, right? They have to be accounted for. And so in this accounting, there's 2 Cl's. And so when I rewrote it in its ionic form, the total ionic equation, then I had to put that 2 in there to account for both of them. Okay? So are you seeing that knowing the oxidation numbers of a atom becomes important? And we started learning, I gave you guys some rules early on when we started naming, because you really need that for naming too. And so what you're going to find a lot of in this course, if you don't get it the first time, then we continually revisit it, right? Because we have to apply it. And so over time you build skills and you don't even realize it, right? Nothing tickles me more than to have one of my student assistants walk in my office and say, oh my gosh, I was helping a Gen Chem student today and they couldn't figure out charge, right? Or some statement like that. And I'll say, do you remember sitting in my office 2 years ago as a Gen Chem student? And what were you doing? I was trying to figure out charge. You with me? And it grows and you don't even know when you learn it, okay? And then all of a sudden you're teaching it to someone else. And so there's a lot of that happens with chemistry. All right, so anyway, we finished that basically, okay? We have the right-hand part down below, and so that completed that. All right, now.
Well, you said we have to balance it.
Yeah, but actually in this case, what? It's already balanced, okay? So this one's balanced. So it's all ones in front of those. And so it's balanced, and so what we're practicing right now, writing balanced chemical equations, is the beginning of stoichiometry, okay? You have to have a balanced equation to do quantities of reactants and products, okay? You have to be able to write these. What are you going to practice on this week? Stoichiometry, but also ions, right? Charge, right? Knowing what they are, knowing the names of the polyatomic ions, those don't go away. You gotta learn those things. All right, the first test is over. You needed them a little bit for the naming. Now we're gonna actually start using them. So if you don't have them down yet, start practicing. And which ones should you learn first? The 8s, right? All the 8s: nitrate, sulfate, phosphate, chlorate, acetate, all right? And if you know those and you find one that has one less oxygen, it's called what? Ite. And if it has 2 less oxygens, hypoite. And if it has 1 more, then it's the perate, right? And so if you learn that naming system in the 8s, those are you can go anywhere from there, right? It's an understanding of the system. Maybe it doesn't make sense to you, but I'm going to repeat that 4 or 5 times in the next few weeks and trying to get you to learn that, okay? Convince you, and then we'll use those. But the beginning of stoichiometry is to do what we're doing, but it's actually the math, the quantitative relationships relative to the reactants and products in the reaction, okay? And so stoichiometry, fun word, right? Mm-hmm. All right. The mole and chemical reactions, the macro and nano connections. All right. There's a number of ways to read this sentence. All right. A number of ways. You could say 2 hydrogen molecules, my bad, react with 1 molecule of oxygen to yield 2 molecules of what? Water, okay? So you could read it in that way. Or you could say 2 moles of hydrogen gas react with 1 mole of oxygen, right? To yield 2 moles of water, or 2 moles of water. Right? You guys with me? You realize that it's just a ratio, isn't it? In the second case, I could even say 2 grams of hydrogen reacts with, no, wait a minute, that's not right. Oh yeah, 2 grams. Reacts with 32 grams of oxygen, right? To yield how many grams of water? 16 times 2 is 32 plus 4?
Yeah.
Yep. Or plus, not 4, 2, excuse me. No, 4. 4, yep, because it's 2 moles. Right? Yeah. About messed that one up. And so I can actually do it by grams because the ratio math there is pretty simple, isn't it? Okay? 4 grams of water plus 32 grams of oxygen yields 36 grams of water. I may have said that wrong initially, so forgive me if I did. All right? Forgive me if I did. All right, how about this one? Kilomoles. Can we use kilo instead? Yeah, because we just multiply everything by what? 1,000, right? And so if we multiply the 4 grams, then we would have 4,000 grams, right? Same ratio, isn't it? How about millimoles if we go to really small amounts? When I was doing biochemistry at University of Kansas, I was actually doing analytical chemistry in a pharmaceutical chemistry lab. Everything we worked with was nanomolar, right? We did everything in nanomole scale, and so could I use nano here instead of micro or milli? Yeah. Or can I use? Yeah. All right. Oh, well, here's the gram thing, right? You guys know how I got to that, right? I took the periodic table conversion and took 2 hydrogens and times 1 each. And because there's 2 of them, then it's 4 grams. All right? So these are relationships that just should become automatic, right? They're pretty straightforward. Now, all of the math that we're going to be doing goes through this mole ratio. All of the math that we're going to be doing in this chapter goes through a mole ratio. All right? And this is kind of a summarized form of that. So what we were looking at right there was from here to here. Okay? We had moles of hydrogen to moles of water. Moles of oxygen to moles of water. Right? Or if we have the moles of water, then we could get moles of hydrogen. Balanced, right? Now, we back up and we go to grams. If I know the grams of hydrogen, can I take the grams of hydrogen and convert that to moles? If I have 2 grams of hydrogen, how many moles do I have? 1 mole, right? And then I go from there to moles, right? And then from there to water moles, how many water moles would I have? 1 mole, right? And to go from here to there, then I would multiply it by the molecular weight of water and get the grams of water. 18 grams of water. Right? From 4 grams of hydrogen, I can make 18 grams of water. Where does the rest of the mass come from? Where does the rest of the mass come from? Oxygen. Yeah. Cool? All right. I'll just let you read there. She's got some good advice. All right. In reality, I want you to print this slide too. Okay? If you don't already have this down, this is a roadmap. Okay? It's a roadmap for all of these calculations. You, depending on what you have, you can go anywhere in this. Okay? So, what we were talking about on the 2 slides ago was going from grams to moles, right? And then through the balanced equation, the moles of something else, and then we could go back to grams. That's what it was showing. But in reality, we could start with the concentration of something, which is right here, and its volume, And so if I have concentration and volume, then I can get to moles, right? In moles per liter. Well, even if I have parts per million, I can convert that to moles per liter, or I can convert it to grams in that amount, and then convert the grams into what? Moles, okay? So, or I can get to molecules if I know the number of molecules. Some reason sapling really likes to do that to you, right? They like to have you tell them the number of molecules, right? Once you get out of this course, then not often will we calculate to the number of molecules, right? It's trying to do it conceptually. Well, all you need is Avogadro's number, right? So if I have the moles of A and I want to get to molecules, in fact, you've already answered that question in sapling chapter 3, right? Yeah, you had moles of something, and then you told the number of molecules. All you had to do was multiply the moles times Avogadro's number, and that would give it to you, right? But if I start at grams of A and go through moles of A, and I know the volume that I'm putting it in, right? Can I calculate the concentration of the solution I just made? You see, I didn't go to the other side that time, did I? This is a roadmap for making solutions too. So you go into the stock room and you get out quantity of sodium chloride, for example, gram amount. And I know what grams I weighed out. I know the volume that I put it in. And so, well, I can calculate the moles and then divide by volume and have molarity, right? The concentration unit of chemists. Right, the concentration unit of chemists are one of them, but one that's very, very popular. All right, so let's actually try some math problems with this. Okay, let's try some math problems with this. Do we have a balanced reaction? There is one up there, isn't there? Yeah. Yeah, I can't hide that. So, all right. So we take a balanced reaction. How much product can be made if 10 grams of aluminum is oxidized? Right? So what is that? There's actually something that's written into that question, and I want to talk about it for a second. What's the limiting reagent? Aluminum, because it's giving you a gram amount, right? So that means, what does it mean about the oxygen? You have as much as you need, it's in excess, right? And so the limiting reagent is saying we have as much oxygen as we need. And so chemists do this to you all the time. They don't say that the oxygen is in excess. They just give you a value and say how much can you make, how much product can you make from this amount, right? Well, as long as the oxygen is in excess, then we can calculate that very easily, right? So how am I starting this? I'm going to start with the 10 grams of aluminum, and this is just a series of conversions, isn't it? Is this a series of conversions? Yeah. So how do I get to moles? I've got 10 grams of aluminum. I'm going to go up and get 1 mole over what? 26.9. You can do 27. I would, but I took your number. So what's the first thing I've done? I took moles of A and what? Or grams of A and did what? Sorry. And I converted it to moles. That's the step from right here. From there to there. How do I get to here? I need a what? A mole ratio. And where do I get it from? Balance equation. So my balance equation says that for every 4 aluminums, right? How many moles of product do I make? 2 moles. And then what's next? So I've now moved to right here. And it's asking for the number of grams. How do I get to there? From moles of aluminum oxide to grams, I use what? The molecular weight. Yep. So I need the molecular weight for aluminum oxide. Can you guys calculate that for me real quick? Two aluminums times 27, and 3 oxygens times 16. Check and see if you get the same answer. 102 grams per mole. So, now we've made the step up, okay? And now you notice I put it all in one calculation, didn't I? Right? Is that normal? Yeah, sometimes. Whatever's most convenient, unless you need an intermediate like you need the moles of aluminum, right? I might stop it here because then I can tell you how much oxygen I needed to react with it, right? It depends on what the question is. And sometimes it has you go in multiple directions. But if I'm looking at this, have we got an answer yet? 18.9. Let's go check that. So we went from aluminum grams to moles of aluminum to moles of product, and then moles of product to grams of product. Those are the 3 steps we made. And so what we actually have done is calculated the theoretical yield for 10 grams of aluminum. How much could we make if the reaction were 100% efficient, right? And then from that, we can actually do the reaction, find out what we actually would make. Are all reactions perfect? And 100% yield is produced? No, seldom are they. So we can calculate what's called a percent yield from that. The expected value, right? And the actual value. And so we'll learn how to do that also in this chapter. But anyway, 10 grams of aluminum to 0.371 moles of aluminum, 3.71 moles to moles of aluminum oxide, and then 1.86 moles of aluminum oxide to 18.9 grams of aluminum oxide. Cool? Yeah. We're going to do these over and over again, okay? And so try to get the hang of them. If you need help with these, we'll come back, and I love it that we ended there because we'll come back and do some more problems off the same one to review this on Wednesday. Okay? We'll do this in review on Wednesday. Have a great day, guys. Kind of quiet today. Long weekend. Must have been at the Cowboys lost. You're so proud.